Okay, so in last video, we give you some introduction about analogy between brains and neural networks. So in this video, I'm gonna give you more specified example of how to use the deep neural networks for classification for multiple labels. For example, if we want to classify the digits, minutes data in the digits. Okay. And we have the input layer, we have one hidden layer, and we have output. And here, the output, we have the 10 labels, right? So after you train your model, so for each given picture with the pixels, 28 times 28 pixels, you need to give the probabilities for each of the Z1 to Z10. And then your model picks the label with largest probability. So in that case, we need a function. So in that case, the final activation function we need is the softmax function. So when m is greater and equals to 2, okay, we can construct softmax units. Okay, for example, if we do the regression, the final layer output will be this W times H, right? W times H. Suppose we call this is a T. This is the vector. This is belongs to. This is so this T. So think about this W. W is a matrix with M times K plus 1 times H, number of the hidden layers, plus the Bayes term. So it's K plus 1. So this T will be a vector of the M dimension. Actually, the softmax activation function is given by so for example, for the first label, what's the probability to predict 0? So Z1 equals to e to the power t1, okay? The first component of this t divided by the summation of the e to the power t1 plus e to the power t2 plus e to the power t10. In general, we have the tm. Okay, so and then we do the same operations for each class. In general, so we get zi equals to e to the power s component of this vector divided by summation j from 1 to m e to the power tj. So now after this transformation, so we obtain that each zi is a number between 0 and 1. Okay, and also maybe let's write down the last one. So z10 equals to e to the power t10 divided by the summation j from 1 to m e to the power tj. And we can say that each zi output is a number between 0 and 1 represents a probability this transformed case is in this label, and also the summation of all this zi. if you summation all the probabilities from the labeled number 0 to number m, you should get the probability 1, right? It must be one of the class. So this Zi represents the posterior probability, the input. So this Zi represents the posterior probability. The input belongs to class I. And note that in general, for the classification methods, we want to choose label highly recommend. Highly recommend to pick label. So that the summation yi, I from 1 to k equals to 1. Okay, so a lot of cases, for example, the output here we can use the label if this is labeled 3, right? This is labeled 5. This is labeled 8. One trick we can do is maybe we can use 0, label 1, 2, 9. For each label we summation those together. So you summation 0 up to 9, and 0 divided by this is the first unit is 0. The second one is 1 over the summation 1 plus up to 9. Okay, and 9 over 0 plus 9. Okay, because we need to calculate the loss function, right? So each of the data set we need to give some training true values. But here for the classification using the softmax is recommended using this. This is not k. This should be m in our example. And then we can choose the loss function. Pick loss function. Pick loss function. So for a k class, softmax output, the loss function between z and y. Okay, so in this, for our example, we have z1 up to z10, right? So for each input value, after we transformation from our training model, we get 10 numbers here, and the summation should be equal to 1. And we also have the y is label, we normalize it from y1 to y10. So each is a vector, and then what we do is we calculate the entropy loss. It's called cross entropy. Cross entropy loss equals to negative summation yi. Okay, and take the natural log zi, I from 1 to m. So for each of the class labels, you check this entropy loss, which means the similarity between yi and zi. Okay, the reason why we pick this cross entropy loss is because when m is 2, this is equivalent to the logistic regression. Okay. And then we apply the stochastic gradient descent algorithm to find V and W from all the weights. So again, we still apply the neural network with one hidden layer. Okay, in order to use the stochastic gradient descent algorithm, we need to calculate the gradients, right? And we're gonna apply the backpropagation. So here in the following, I will show you the algorithms for the softmax backpropagation. Okay, softmax propagation, and in the following algorithm, we require that with the assumption that your label you add together should equals to 1. Okay, so